until level 9, right? If you are able to do some revisions, then I think you are able to maintain at level 9. If not, then maybe it's a bit difficult to maintain at level 9, but you have the solution. The solution is to run the revision, right? The revision is, you have a few steps. You have 4 steps actually. So once you understand, you remember the main drawer, the main story of to help you to remember the drawers, and that is level 1, step 1 and step 2. Then for each drawer, you have the story. In each drawer, there are 5 drawers, and that will help you to remember the content in each drawer, right? And I also created this AI generated animations to help you to remember the story easier, right? I hope that will be able to help you to be ready when you need to understand what, in more detail what is in the chapter, and help you to be able to remember what is the content in each of the drawer, right? So let's go to our next chapter. Next chapter is quantum physics. Start time is 6 a.m. Okay, my time is 6 a.m. Quantum physics is actually the last chapter of Form 5. Form 5 is year 11. And by end of this year, Xingling is going to take an exam. And this is the last chapter of the physics in SPM. There are 5 drawers. Drawer 1, drawer 2, drawer 3, drawer 4, and drawer 5 are all listed over here. So let's continue on step 1. We have Genesis, theory of light and photons, wave particle duality, photoelectric effect, Einstein photoelectric theory, not effect. Right. So how do we remember this drawer name in sequence? Ganesh drive proton car into wave party, took photo with Einstein's EV, electric vehicle. For Xingling, I'm sure you know what is. I'm sure you know the car Proton. For Aiden, Proton is a car manufactured by Malaysia. It's a Malaysian national car. You came to Malaysia before. I believe that you might have seen some of the Proton car. If you realize, if not, then just remember there is this car with the brand name called Proton in Malaysia, right? So Ganesh is a very common name in the Indian community in Malaysia also. I'm not sure about the Indian community in Canada, but that's how I use Ganesh, right? In fact, I have a friend called Ganesh also. So that Ganesh, the name is to reflect Genesis, right? So Ganesh drive proton. Proton is to reflect photon. Then he drive the proton car and into a wave party. So there's a wave party, and wave party obviously is to reflect wave particle, right? Wave particle, and then took photo. He went into the party and took photo. Photo is photoelectric effect. It took photo with who? With Einstein's EV, electric vehicle, right? Einstein, why EV? Because it's photoelectric, right? So imagine Ganesh drive for proton car, or drive his proton into wave party and took photo with Einstein EV. Let's try to see this.
Form 5, Chapter 7, Quantum Physics. Ganesh drives proton car into wave party. Took photos with Einstein. Draw 1. Genesis. Black body glows ultra.
Wait, something is wrong with my YouTube. Let me just wait for it to refresh a bit. Then we'll see the animations, and this will help you to remember the story, the Ganesh story that went into this wave party. Where's it? Hang. It's okay. Let's try again. I'll play again.
Form 5, Chapter 7, Quantum Physics. Ganesh drives proton car into wave party. Took photos with Einstein. Draw 1.
Okay. Are you able to see the video just now? There's an elephant with the proton car. Yes. Okay. Singing, are you able to see it? If not, let me send this. Okay, good. At the same time, I'm also sending this link. I'm also sending this link in the chat. It's really laggy. Right. If you can click this link, and let's see what watch the video for the first 15 seconds. I'll give you. Let's try it. Let's try it. I send it in the chat. I'll try to play this video again. No, let you play the video, so I will not interfere. Okay. If you have done playing the video, let me know. Then we can continue. Are you able to play the video? Anyone? Yes, Aiden is able to play the video. So is it still laggy from your side after I gave you the link and you play it from the link? Okay, excellent. So I believe you have already watched the story for that 10, 11 seconds, and that will help you to remember this story. Right, Ganesh drive a proton car, or drive his proton car and go into this wave party, and took photo with Einstein's EV. Right, so that is to reflect the drawer's name. Ganesh is Einstein. Proton, photon. Wave party, wave particle duality. Took photo, photo is photoelectric effect. Einstein EV is Einstein photoelectric theory. Now let's go to step number 2. Step number 2, they're also divided into 5 drawers. And each drawer you have maybe 2 or 3 points that you need to focus on. So as usual, I think we have been doing this for like either more than 10 times. I'll give you a few minutes for you to read, and let's set the expectation. Do not expect yourself to fully understand everything you read in step 2, right? You're still in step 2. So expect that you are in the level of 2, let's say, out of 10. Okay, what does it mean? It means that you just need to know that there are 5 drawers, and each drawer there are a few points that you need to learn in the following steps. If you can understand some of the keywords, then it's excellent. If not, you just need to know that there are some keywords, the new terms, or a new formula that you need to know later, right? So let's start with a few minutes. See how. Okay, let's read from drawer 1 to drawer 2 first. Okay, for 1 minute. Okay, let's start now. Drawer 1 and drawer 2. You should be in drawer 2 now. All right, time's up. Like I said, if you do not fully understand, that is fine. Right, let's do drawer 3 until drawer 4. Drawer 3 until drawer 5 for 2 minutes. Right, for 2 minutes. Let's start now. You should be in drawer 4 or 5. Maybe, yeah, 4 now. You should be in drawer 4 now. Okay, you should be in drawer 5 now. Or if you finish reading it, you can read the whole step 2 again, just to make you familiarize. There are 5 drawers, and what are the key terms or key points in each of the drawer. Right, 10 more seconds. Okay, time's up. So there are 5 drawers: Genesis, photon, wave particle duality, photoelectric effect, Einstein photoelectric theory. Ganesh drive his proton car into wave party and took a photo with Einstein EV. Right, I hope when I read this out, you can imagine that 10-second short video to help you to remember the 5 drawer easier, right? So now you are at, after step 2, you're at level 2. Level 2. Level 2 is not to expect you to know everything. Level 2 to expect you to know there are at least 5 drawers, and there are at least a few points, right? Like 2 points, 3 points for each of the drawers, right? As long as you know that there are 2 points or 3 points, that's enough. You don't need to fully understand what are these 3 points and what are these 2 points and what are these 3 points, right? You know that you're going to learn some 2 new formulas over here for drawer 3 and drawer 5, and some definitions for drawer 1 and drawer 2, and also drawer 3, also drawer 4, right? So let's move on to step 3 with the intention to increase, to up level your level from 2 to 3, right? I'm going to repeat myself again that the step 3, how do you reach step 3? Step 3 and what's the relationship between step 3 and step 2? Step 3 and step 2 is an extension. Step 3 is an extension of step 2. So if you realize, this is also talking about the genesis, and there are also 2 points, right? 2 points, limitation of classical theory and the black body, right? There are also 2 points, and these 2 points is helping you to level up. If you play game, you know, to level up from level 2 to level 3, okay? So let's do slowly. Let's do 1 minute first, 1 minute, one by one. Okay, for drawer 1 and point number 1, right? Drawer 1 and point number 1. So I will leave the step 2 here on your right, and on your left is the step 3. So you just need to read step 3 and also link it with what you have read just now in step 2. Let's start now, 1 minute. For drawer 1, point number 1. Okay, you should be reading the black body by now. All right, that's point number 1. You should now have a little bit more understanding about the classical theory. You may not fully understand this one once you read this short paragraph. If you do, then excellent. If you do not, then it's fine. You're going to read it later more. It's related to the frequency and intensity, and also the energy. Right. Last time the physics taught some wrong assumptions, and then later the more modern physicists corrected this. Right. This was the classical physics. Then you have the more modern physics to correct what was being assumed, which is wrong. Right. Then there is some black body definition that you have read just now. So that will help you to increase your level of understanding from 2 to 3. Right. And 3 is still a very low level, so don't expect yourself to fully understand everything. Right. So let's read this point number 2 about the scientists. Let's start now. Okay, time's up. How do you read this? Do not read you do not need to remember all the names, right? This table is divided into the classical physics and also the more modern physics, or we call it quantum theory, quantum physics. So from about Max Planck onwards, this is the more modern one. The Thomson and below, and early from Isaac Newton. This is the classical physics, right? So after that, they discover photons, then they are able to explain photoelectric effects, like by Einstein over here. For Max Planck, they are able to understand the quanta, which is related to discrete energy, which is related to photon that you're gonna learn in drawer 2. And then you have this wave and particles duality, which is you're gonna learn in drawer 3, right? Which is being discovered by or explained better by the Broglie, Louis de Broglie, right? So we divided into this Max Planck before and after. Now, that is drawer number 1. So your level should increase by 3 now. 3 is still a very low level, so don't worry about understanding the whole thing now. Okay, so because there are so many formulas over here, so let's do it slowly for 2 minutes rather than 1 minute. Okay, drawer 2, start now. It should be in point 2 by now. You should be in point 3 by now. Fifteen seconds. All right, time's up. Okay, don't don't worry about if you do not understand the formula. Let's understand the concept. What is this drawer is about? This drawer is to introduce this quanta. Quanta is a type of energy, right? And then later it's being identified as a photons. How do you calculate this? Using this formula. E equivalent to HF, right? E is the energy, HF, right? Then you have this, H is the Planck constant. So it's a constant, which is 6.63 times 10 to the power of minus 34. Then F is being defined, is a frequency. Frequency you can define using the speed and also the wavelength. This I think we learned in the chapter wave, if you still remember, the relationship between wavelength, frequency, and the speed. So we're talking about the speed of what? The speed of light. Okay, we're talking about the speed of light, so it's 3 to the power of 10, 3 times 10 to the power of 8. Right. So this is how you are able to calculate the energy of a photon. Right, this is one example. Then if you have many photons, then you times n, right? And number of photons, the energy that is being transmitted. This is single photon, this is more than one photons. And that's it. All right. And again, we are expecting you to increase to the level of 3 only. We are not expecting you to be at level 9 or level 10 by now. Okay, you just need to know there is a definitions, and you know a little bit more what is photon, what is quanta of energy. And also you know there's this formula. And this formula is not too complicated. It's E equivalent to HF. That's it. H is the Planck constant, which is a constant number. And it's written over here. And then F is a frequency, and you can define the frequency using the speed and also the wavelength, and that's it, right? So let's do the same thing for 2 minutes for drawer 3. Let me just scroll down a bit for you to also able to refer on your right, which is the step 2. Okay, let's do it now. 2 minutes, drawer 3. Okay, you should be in point 2 by now. Should be in point 3 by now. If you finish reading, then you can read it again if you want. Okay, 15 seconds. You can actually write down in a pen or on your paper on the formula, because it's only a few formulas. And you will come in handy when you try to refer this formula later. Right, so Broglie hypothesis, this is wave-particle duality. What does it mean? I hope you still remember what is wave and what is characteristic of wave when we learn this in the chapter in Form 4. Right, so wave is able to diffract, wave is able to reflect, and wave is able to refract. But particles, let's say you have a ball right in front of you. Can you imagine the ball is able to diffract? Right, it's quite impossible, right? It cannot be diffracted because particles like a ball cannot be diffracted. However, Broglie is able to prove that there is this wave-particle duality. So you have your electron is able to perform like a wave characteristic that it can diffract. Right. So that electron, imagine that it is a ball, it can be diffracted. Right. So that is what is trying to explain over here in drawer 3. Right. And there's a formula that's related to this drawer 3. And there's an applications. right? These electron microscopes is able to have a higher magnifications and resolutions compared to an optical microscopes. So that is to help us as human to be able to see a more detailed image of a structure like red blood cells. Okay, that's how you apply this wave and particle duality and turn it into an application, which is called electron microscopes, right? So that is drawer 3. So I hope now your level increase to level 3. Right, we know a little bit about what is this wave particle duality. So let's go to drawer 4. 2 minutes, start now. Okay, you should be in point 2 by now, the characteristics. Thirty seconds. Seconds. Right, drawer 4 is even easier. Easier as in there are 2 points only, rather than 3 points. Definition, characteristics. That's all you need to know, all right, to move yourself from level 2 to level 3. And there's something related to something pops out, right? The photoelectron being pops out, that means emission. And how is it being pops out? When it reaches a certain frequency, and then it will pops out. Okay, so that's the definition for this photoelectric effect. Then there's these characteristics. There are 4 characteristics of photoelectric effect. Something related to threshold frequency, instantaneous emission. It's not gradual. It just pops out like that. Once it reaches the frequency, then something pops out, which we call photoelectron. There's electron that pops out. And that group of electrons that pops out are named photoelectrons. Right, then there's this intensity versus current. So what does it mean? And also the frequency versus kinetic energy. What does it mean? So there are 4 characteristics. You don't need to memorize this now. You just need to know there is such thing as 4 characteristics in drawer 4 that you need to know. Okay, and it's related to frequency, related to instantaneous emission, related to intensity, related to kinetic energy. Okay, so let's go to the last drawer. Let's do 2 minutes. Start now. You can write down this formula on your paper if you want, because it's easier for you to refer later. You should be on point 2 now. Thirty seconds. Ten seconds. All right. So what do you have inside here? I think the most important part is the work function. Work function is the minimum energy required to release an electron. Just imagine if there is you need to release something. Oh, let's say a ball is being stuck in a hole, right? Being stuck somewhere. There is a minimum force that you need to push the ball to pop out from that wall that is being stuck inside the wall or inside the fence or a door, right? In the bit is being stuck somewhere. There's a minimum energy that you need to exert on the ball to be able to release the ball out from that thing that is being stuck into. So that is the work function. Okay. Now let's move to step 4. Let's move to step 4. Okay, and drawer number 1. Step 4. We have this. Yeah, we have 2 questions for each drawer. So once you read this, you have to set the own expectation that you are increasing your understanding level from 3 to 4, right? After you read question 2 and question 1 and question 2, right? So let's do 2 minutes for question 1. Draw 1, start now. All right, 30 seconds. I hope by now your understanding level is increased from 3 to, let's say, 3.5. 10 more seconds. Okay, classical physics is talking about if you increase the frequency, the energy will increase together with the frequency. And if the frequency is infinite, then the energy will be infinite, right? But that is what we call this is wrong, and this is what we call ultraviolet catastrophe. So wavelength is inversely proportional to frequency. That means the shorter wavelength, the higher the frequency, right? So if the frequency and the energy is proportional, that means what is being explained before as classical physics, the higher, the more infinite the frequency, the more infinite the energy, then this graph should go up. It's not going down, should not be going down. But the fact is, this graph, which is being defined by the and explained by the modern physics, that is, it is not going up infinitely, right? So that is the myth, or that is the burst of how modern physics is explaining what classical physics is unable to explain. Okay, there is this very short question number 2. Okay, let's read it in 1 minute and start now. Okay, 10 more seconds. Okay, so I hope your understanding level for draw 1 increased to level 4. And draw 1 is about the genesis. That means the original, the classical physics, right? It's talking about the classical physics theory and also black body, right? So let's go to draw 2, and with the intention to increase your understanding level to level 4. Okay, let's do 3 minutes for the two questions. Let's start now. Okay, 3 minutes starts now. If you finish reading, then you can read again, because you have 3 minutes. With the intention to improve from level 3 to level 4. Okay, 1 more minute. $20. All right, time's up. So that's drawer 2. It's about photon. Right. In the main story, you remember Ganesh drive his proton, the car. So that is to help you to remember the genesis and also the photon. Right. And these two questions, 3 and 4, is to explain what is quanta and what is the difference between intensity and frequency. So I hope you have more understanding about what is the difference between frequency and intensity by now by reading this. And if you realize in step 2, this is the summary of what you read in step 3 just now. Energy increase with frequency. And for intensity depends on the number of photons, right? So photon power is like a photon power. And then energy increase with frequency, right? Because there is this, how the energy is being defined as a formula for the photon energy is E equivalent to HF. So there's F here. F is able to, the higher the F, the higher the E. So the higher the F frequency, the higher the E energy, right? So let's move to drawer 3. Drawer 3 also will give you 3 minutes. Let's do 3 minutes. Let's start now. Okay, you should be in question 6 by now. One more minute. Okay, 30 seconds to increase your level from 3 to 4. $20. Okay, so that is the wave particles duality. Electron is able to perform this wave. We are able to see this wave characteristic because it is so tiny. The wavelength is 1,000 to 10,000 times smaller than the visible light. Right, that's why you can see, you can display this type of characteristic like a wave characteristic, even though it is a particle. Right, let's go to drawer number 4. Same thing, we'll do 3 minutes for drawer number 4. Let me just throw up a bit here for reference. Let's start now. Okay, 30 more seconds. We'll go for a short break after the draw 5. Ten more seconds. All right. Quantum physics is something that you do not apply every day. So that's why sometimes maybe you feel that it is a bit hard to understand. And that is fine. We'll help you to improve it to a higher level slowly. All right. It's not like pressure or force that you apply it every day in your life. So let's go to drawer 5. We'll get also 3 minutes because there are so many weird formulas. So let's read it slowly. Right, you should be in question 10 by now. Okay, time's up. Okay, I think it burns quite a bit of your brain cell by now. Let's go for a rest for 5 minutes for your water break and for your toilet break. Start now. All right, are you guys back? Can I see a show of hand? Okay, Sim is back. Hayden, are you back? Yep, both are back. All right. I'm not sure how do you feel if it is something difficult to understand or it is something still okay. Right. I think because it is not something that you apply every day in life. So maybe to associate it with what you're applying in life every day, like other chapters, like forces and motion, pressure, electricity. Maybe it's a bit more difficult to relate, right? But it's fine. I think the content inside each drawer is not too heavy, right? If you break it down, there are 5 drawers, and each drawer, if you break it down, drawer number 1 is talking about before and after. Before and after. So classical theory and the quantum theory, which is the new one, right? So Max Planck is the new part. Before Max Planck is the classical part. If this is able to help you to understand better, and that's it, right? It's about the genesis of quantum theory. Then drawer number 2 is about the photon energy. Everything is about how this photon energy is being defined. How do you calculate them? What is the and the 2 main thing is what's the difference between intensity and frequency, right? And these 2 sentence or these 2 points summarize it, right? Energy is frequency. It's increased with frequency. Then the intensity depends on the number of photons, and that's it, right? So don't overcomplicate your understanding at this point of time because we are still at level 4. Once you read step 5 to bring it to level 5, then you will have a clearer idea, right? Then let's continue, which is drawer 3. This is the Bernoulli's hypothesis. This is the wave and particle duality. The electron can also act like a wave, right? Can human act like a wave? Cannot. We cannot be diffracted, right? Can a football act like a wave? It cannot be diffracted. You cannot imagine the ball is being diffracted. Can water act like a wave? Yes, because water is water is not particle, right? But electron is like a particle, but it can, and it's proven that it can act like a wave, right? Why it can act like a wave? Because the wavelength is so much smaller. That's why it is able to act like a wave. And there's this formula over here. So that's about it, about this drawer number 3. Then drawer number 4, photoelectric effect. You have the definition of photoelectric, and then you have the characteristics, right? What's the definition? It's light ejects electrons with frequency that is high enough, right? Then there's these characteristics that's depending on the frequency, depending on the current intensity, and the instant emission. Then this the last drawer is the work function. Mainly is the work function and the threshold frequency. It's all about this formula. All right. So let's continue to increase the level from 4 to 5. Right, 4 to 5. For drawer number 1, there is this part over here. So by the okay, let's do 3 minutes, but I'm going to slow down slowly, gradually to max Planck. Okay, from drawer 1 to max Planck. Okay, let's start now. I'll scroll down slowly. All right, time's up. Okay, I hope by reading this now, it increased your level from 4 to 5, right? About drawer 1 Genesis. So let's continue to drawer 2. Okay, drawer 2 is also, we'll do 3 minutes, right? Drawer 2 is about the photon electron. No, sorry, the photon energy, right? The photon energy. Let's start now. One more minute. Okay, 5 more seconds. All right. So I hope you realize that this step 5 is also an extension of step 2. So you see, you have mathematical framework over here. You have only 4 words to explain this mathematical framework in step 2, but you have a ton of informations over here. Okay, to explain what is this mathematical framework they're trying to explain over here. And photon power, same photon power. And rather than just reading this one short sentence, it is giving you a whole lot more content to help you to understand what is photon power and help you to understand what is drawer 2 generally all about, right? To move you from level 4 to level 5, right? So now let's do the same thing for drawer 3 and to move you from level 4 to level 5. Okay, let's do also 3 minutes. Let's start now. One more minute. More seconds. All right. I hope by now your level 1, 2, 3 is your drawer 1, 2, 3 is at level 5. Now let's do drawer 4 and also 3 minutes. 3 minutes. Let's start now. 30 seconds. All right. Okay, time's up. This is drawer 4. Okay, let's before we go to drawer 5, let's see to refresh our main story again. Ganesh drive his car, which is Proton, into a wave party and take a photo with Einstein EV car, right? And that is helping you to remember there are 5 drawers and what are the name of the 5 drawers. So we are in drawer 4, which is photoelectric. In that main story is the photo, right? Einstein is taking a photo. Ganesh is taking a photo with who? With Einstein's EV car. So Einstein's photoelectric theory. All right. So let's do this. Then we'll go to step 3. Step 6. Let's do this in also 3 minutes. Let's continue the same trend. Thirty seconds. We're almost there. All right. The most boring part, the reading part, is almost done. All right. So let's do a quick review. We have 5 drawers, and we have this story, and you also played the animation, the video for the 10 seconds to help you to remember, because the animation will help you to remember this story easier rather than you reading this short sentence to imagine by yourself. We have done that for you. Then each of the drawer will have their own key points, And the key point is simple. Some are having 2, some are having 3. Not like other chapter, there's some of the drawers are even having 6 or 5 key points. Right? So do a quick review. Number 1 drawer is talking about the difference between, or is explaining you the classical physics. And there's this catastrophe, we call it ultraviolet catastrophe. Right, then there's something related to the black body. And that's where they are also comparing the Max Planck, Albert Einstein, their findings, which is related to the quantum theory. The one that is before that, they are the classical theories, which is having a big flaws, and that flaws is called ultraviolet catastrophe. Right, and what is this flaw? The flaw is about this, if you read here. Classical physics predicts infinite energy at high frequency, which contradicts with the experiment. Then drawer number 2 is the photon. You know, there is this formula, and then there is something related to the frequency and intensity. Next is the wave particle duality. This is the wave party, right? And that is this key information, the 3 key information that's related to the key to the drawer number 3. Drawer number 4, photoelectric effects. So there is a definition and there's a characteristics. The characteristic is related to the intensity, the frequency, right? And also it's related to the instantaneous emission. Okay. Then the last one is you just read the photoelectric theory for Einstein. So now, with that, we'll move to step 6. Step 6, this is the story. Let me explain my story, and then let's see whether this can stick and to you can make it relevant to the key points that you have read just now for each of the drawer. So each drawer number 1, black body glows ultraviolet light, then drop down and Planck. So imagine there's a black body, it glows ultraviolet. So ultraviolet is a type of light, right? Like a blue color ultraviolet light or purple color. So that black body glows ultraviolet, then the black body drop down and do Planck. Right, I think with these keywords, you already have some idea why I created this story. This story is to help you to remember that there is something related to black body in drawer number 1. And then there is this ultraviolet catastrophe that we explained just now. And it drops, if you remember the graph that we saw. Let me just refer it back to the graph. Okay, right, this drop down, you see this drop down. Classical physics is explained, it will go up infinitely. But in the experiment, it shows that it did not increase infinitely, but it drops down. Right, so this is the drop. So that's why my story has a drop down. Okay, let me throw it back. Okay. And then when the black body drop down, he does Planck. You know the exercise Planck? Right, that Planck is to relate to Max Planck, the name Max Planck. Right, so this is the story for drawer number 1, to help us to remember certain key concepts or keywords that is in drawer number 1. Right, so there's black body, there's ultraviolet, there is something drop down, which is then he did a Planck. Right, drawer number 2 is the photon energy. Right, so what is the story? Many panda lines up to the zoo. Many panda lines up and makes the zoo bright. And this is the formula. Why many panda? Many photon, right? Many photon. Y lines up, they are queuing in the line. Line is the line spectrum that we learned just now, like line spectrum and continuous spectrum. So this is to help us to remember that part. And makes the zoo bright. So photon, number of photons or number of panda is the intensity, right? Intensity. And then that bright is to relate with the frequency and also intensity. So there are two types of way to describe the photon energy, which is frequency and intensity. Draw number 3 is bro wave goodbye to ball. So your brother wave goodbye to a ball, and the ball diffracted. And then once it diffracted, it hits microscope. So this bro is to reflect there's this Broglie, right? Broglie hypothesis. And then the wave goodbye is the wave and particle duality, right? To remember that. And then wave goodbye to a ball. Ball is the electron, right? Electron, which is supposed to be a particle, but it can be diffracted. So that in that story, the when you wave goodbye, or when your brother wave goodbye to the ball, and the ball suddenly diffracted. When it diffracted, it hits the microscope, and that microscope is to explain the electron microscopes, the applications that we use from this concept that help us to be able to see something that is so tiny like red blood cell better. Right, then there's this formula. This is the formula, the lambda formula, this one. You have to remember this. If you have a pen and paper, just write it down. Photoelectric effect. Light shines at metal's eye, reach threshold, it pops out instantly and move fast to emergency. Right, what does it mean? So you remember the photoelectric effect, how does it work? You have to exert a certain energy from the light. So you can imagine this torchlight shines on a metal, and that metal's eye, just imagine that metal has an eye, it pops out. So the light shines on the metal's eye, and then it pops out after it reaches a threshold. Right, the eye pops out instantly, right? Not gradually, not slowly popping out from the eye socket, but it pops up instantly, and then move fast to emergency. Right, it is able to move fast and move fast to emergency. That means it moves very fast. Right. Okay. So drawer number 5, Einstein worked hard to earn exit fee and fly away. So this is talking about the work function and the threshold frequency. Einstein, he works very hard, which is work is to reflect the work function. And then he earned the exit fee. Right, exit fee is the minimum threshold that is needed, threshold frequency that is needed to release the electron. And then he fly away. Okay, release the electron means fly away. Okay, so that is the drawer at the story for each of the drawer. So we can watch from the link. Let me try from my side. I hope it's not too laggy by now. Okay, it's only 1 minute and 20 seconds. So let's start watching from the start. I'll start now.
Form 5, Chapter 7, Quantum Physics. Ganesh drives proton car into wave party. Took photos with Einstein. Draw 1. Genesis. Black body glows ultraviolet light. Then drop down and plank. Draw 2. Photon energy. Many panda lineup. Makes the zoo bright. Draw 3. Wave particle. Duality. Bro waves, goodbye to ball. Ball, and it diffracted and hit microscope. Draw 4. Photoelectric. Effect. Light shines at the metal's eye. Reach threshold, it pop out instantly, and move fast to emerge. Draw 5. Einstein's photoelectric theory. Einstein work hard to earn exit fees and fly away.
Right, so this is the picture that I draw to reflect this drawer. Right, but I think the video is better. Right, picture is needed when you are preparing for exam. Right, imagine that now you are able to remember this or able to draw out this picture, and then during the exam you draw this out, then you remember the drawers and remember the story, and that will help you to be able to retrieve the information in the picture or in the drawer and to answer the question in the exam. Right, of course you cannot bring this YouTube link to your exam, and also you cannot remember all these keywords during your exam or write it down on a paper, but it's easier for you to draw something like this in your exam, right? So that you can refer it and to retrieve the informations or the concept from this picture and write it down as an answer to the question in your exam, during your exam. Okay, so that's the reason why we need this picture if you are preparing yourself for an exam like Singlink. End of the year, you'll be sitting for this SPM exam, the big exam for your secondary school. So if you imagine that you are able to draw this picture for the 13 chapters from Form 4 until Form 5. In physics, you have 13 chapters in total. 6 in Form 4, 7 in Form 5. And imagine that you are able to remember this picture, 13 of them, and you draw it out during the exam. And that will help you to be able to retrieve the needed informations to answer all the questions, your exam questions, when you are sitting in an exam hall, right? Because you definitely cannot bring this in, the link. You cannot bring your phone and start watching the animation. And obviously, if you will not be able to remember all the words because words is harder to remember, but picture is easier to remember. So with this picture, you'll be able to easily retrieve information, right? So since we're talking about retrieval of information, and that is one of the main skills to move you from a version B of a student to a version A of a student. So let's go to step 7. And step 7, how do you do this? You read the questions, and then you create your own answer before you read the answer. Once you created your own answer, then you compare with this answer. If it is exactly the same, as in the key information, not exactly the same as in the sentences, then you are fine. If it is not the same, it's still okay. You see what are the new information or concept that you missed, then you intentionally pick it up and learn it and put it inside your drawer number 1. Right? The drawer number 1 is this. Black body glows ultraviolet light, then drop down and plank. Okay. So I have 2 questions for each drawer. So total we have 10 before we go for the video. Right, I think you guys love the video much better than reading. So let's do this for 1 minute. I think 1 minute is good enough for each questions. Let's start now. Question 1. Okay, let's do question 2. Your drawer understanding for drawer 1 should be at 6.5 now. After question 2, you should be 7. All right, let's do drawer 2, photons, 2 questions for 2 minutes. Let's start now. Two minutes. I'm gonna add 1 more minute later. Okay, 1 more minute for drawer 2, question 3, question 4. You should be reading question 4 by now. Ten seconds. All right, let's move to drawer 3 with the intention to help you from level 6 to 7. Let's start now. 2 minutes. Question 5, question 6, right? You should be in drawer question 6 by now. Okay. Drawer 4, photoelectric effect. Let's start now. All right. We are at the last drawer before we go for the video. All right. Let's start now. Draw 5. Thirty seconds. Okay. So let's watch the video. Let me turn on the video. Over the link. Let's hope it doesn't get hang like just now.
Welcome to This Explainer. Today, we're diving headfirst into one of the absolute most thrilling
I hope you're able to watch, to see it, and also to hear the lady was speaking just now, right? Can I see a show of hand?
scientific mysteries in human history. We're going back to a time when the class.
Okay. So let's watch for about 9 minutes. And intentionally, to know that this particular slide is talking about which drawer. Okay? There are 5 drawers.
classical rules, the ones that governed our entire universe, suddenly and completely inexplicably just stopped making sense.
Picture this for a second. You're a brilliant physicist at the dawn of the 20th century. You've got Newton's laws of motion down pat, you totally understand electricity and magnetism, and honestly, you feel like the physical world is pretty much figured out. But then, you try to understand the simple nature of light emitting from hot objects, and the math just completely falls apart. I mean, what actually happens when the foundational laws of physics just outright stop working?
Well, here's our roadmap to figure that out. First, we'll look at the classical failure. Second, enter the photon. Third, wave-particle duality. Fourth, the photoelectric effect. And finally, Einstein's equation.
All right, kicking things off with part 1, the classical failure, when the old rules just stopped working.
For centuries, scientists went back and forth debating the nature of light. In 1704, Isaac Newton was like, it's a stream of particles. But by 1801, Thomas Young does his famous double slit experiment and seems to prove definitively that light is actually a continuous wave. Then in 1897, J.J. Thomson discovers the electron. So by the late 19th century, physicists were feeling incredibly confident in their continuous wave theories. But right at the year 1900, yeah, they hit a massive, unavoidable crisis. So the crisis started with something we call a black body. Basically, a black body is just an idealized object that absorbs all radiation and then emits thermal radiation based purely on how hot it is. Think of the heating element in your oven. Actually, scratch that. Think of it as it gets progressively hotter. It glows, right? It emits this continuous spectrum of light, from infrared all the way up to visible red, then yellow, and so on. But here is the inciting incident of our whole scientific mystery. When physicists used their trusted classical wave theory to calculate the energy coming off that black body, the math basically said that as the wavelength gets shorter, which means the frequency is getting higher, the light energy should increase to literally infinity. But experiments proved the exact opposite. On a graph, instead of shooting straight up into infinity, the actual radiation intensity peaked and then just dropped right off. Classical physics had completely, utterly failed. Which leads us perfectly into part 2. Enter the photon, the radical idea. Now this right here brilliantly illustrates the paradigm shift. I want you to think of the classical theory of continuous energy, kind of like walking up a smooth ramp. You can stand at absolutely any height. But Max Planck, in 1900, steps in and says, actually, energy works a lot more like a flight of stairs. Energy can only exist in discrete, specific little packets called quanta. Albert Einstein would later call these light packets photons. You cannot stand halfway between two steps. Energy isn't this smooth, continuous thing, it's bundled. And here's the kicker. Making a light brighter doesn't make the steps taller. It literally just adds more photons. To actually make this math work, Planck had to introduce a brand new constant. And check out this number, 6.63 times 10 to the power of negative 34 joules seconds. That decimal point has 33 zeros before the 6. I mean, that's Planck's constant. It just goes to show how mind-bogglingly microscopic this discrete quantum energy realm really is. It's so incredibly tiny that to our giant human eyes, the stairs just look like a smooth ramp. But down at the atomic level, the stairs are very, very real. And the energy of a single photon is directly tied to its frequency. Moving right along to part 3, wave-particle duality, the absolute mind-bender of the story. Okay, so in 1924, a physicist named Louis de Broglie totally flips the script on everyone. He proposes this completely wild: if light, which we always thought was a wave, can act like a particle, then physical particles of matter, like electrons, should be able to act like waves. And incredibly, he hit the nail right on the head. By 1927, scientists fired electrons through a super thin layer of graphite and observed a diffraction pattern. That is a behavior that's completely exclusive to waves. Physical matter is literally wavy. Now, you might be wondering, why does this matter to me? Well, because this mind-bending theory has deeply practical real-world implications. An electron's wave is roughly 1,000 to 10,000 times shorter than a light wave. And because that wavelength is so incredibly tight, we can use electrons to achieve massively high magnification. This exact principle is what makes powerful electron microscopes possible. It allows us to clearly see incredibly tiny structures, like the intricate details of a human red blood cell, that a standard light microscope could just never resolve. All right, on to part 4, the photoelectric effect.
the actual experiment that changed everything.
So imagine a photocell inside a vacuum tube. Step 1, a beam of light shines right onto a light-sensitive metal surface. Step 2, an electron inside that metal absorbs a discrete photon of light. Step 3, the electron absorbs just enough energy to break free and is emitted into the circuit, producing a nice electric current. Sounds pretty straightforward, right?
Well, the results were totally bizarre to the classical physicists. See, classical theory dictated that a super bright, really intense light should easily rip electrons away because, it just has more overall energy. But the experiments proved that intensity literally didn't matter at all. You could shine a blindingly bright red light on this metal and absolutely nothing would happen. But a super dim blue light, electrons would instantly shoot off. The kinetic energy of the electrons didn't depend on how bright the light was, but strictly on its frequency. It required a specific minimum threshold frequency to work at all. No way around it.
Which brings us to the grand finale, Part 5, Einstein's photoelectric equation, the masterstroke.
So Albert Einstein actually won his 1921 Nobel Prize for an elegant energy equation that completely solved this puzzle. A core piece of his equation is what's known as the work function. I want you to think of the work function kind of like the entry fee, or the toll, that an electron must pay to escape the metal surface. The incoming photon has to have enough baseline energy, which again is tied to its threshold frequency, just to pay this toll. Let's look at how this applies to the real world. Different metals hold on to their electrons with completely different strengths, which means they have totally different work functions. For example, tantalum has a fairly low work function, so it only requires a lower threshold frequency to release an electron, compared to something like platinum, which holds on to its electrons a whole lot tighter.
Einstein summarized this entire phenomenon in one beautifully simple equation, HF equals W plus Kmax. So what does this actually mean? Well, HF is the total energy of the incoming single photon. When that single photon hits the metal, its energy gets spent in two ways. First, it pays the W, the work function, just to break the electron free. Second, whatever energy happens to be left over becomes the Kmax, the maximum kinetic energy, which basically determines how fast the electron zooms away. One photon transfers its energy to one electron. The whole shebang. Explained. Case closed.
Now, at this point, you're probably thinking, okay, this is great for a physics lab, but what does it actually mean for me? Well, this century-old quantum breakthrough is literally powering our modern world. When sunlight hits a solar panel, it's the photoelectric effect, knocking electrons loose to generate electricity, powering everything from the LED street lamps outside your house to the actual International Space Station. When you walk into a grocery store and those automatic doors magically open, it's because you broke a beam of light, stopping a photoelectric current. Even the camera in your smartphone uses image sensors that rely on these exact same principles to convert physical light into digital pixels. It's everywhere. The foundational rules of classical physics failed, for sure, but the quantum rules that replaced them, they opened up an entirely new universe of possibilities. We've literally gone from being confused by glowing ovens to building solar panels in outer space. So the question I want to leave you with today is this. As we continue to master these incredibly bizarre atomic behaviors, how is quantum mechanics going to drive the next era of technological evolution? With the dawn of super-fast quantum computers and unbreakable encryption algorithms right on the horizon, I'd say the quantum leap has only just begun. Thanks so much for joining me on this explainer, and keep exploring.
All right. I hope that explained a lot and that helps you to increase your level from 7 to 8. Let's go for the last one to increase from 8 to 9. This is going to take maybe
Welcome to
4
today's
to 5
Awesome
minutes.
Deep Dive.
Let's start now.
We are tearing into some classic physics literature today to look at how the entire foundation of classical mechanics just, broke.
Completely fractured. Yeah.
Right. And to visualize where this started, go look in a mirror. The pupil of your eye looks completely black because it absorbs almost all the light that enters it, letting virtually nothing bounce back out.
Mm-hmm.
And physicists call an idealized version of this a black body.
And trying to figure out how these black bodies emit radiation when they get heated up is exactly what fractured our understanding of the universe.
Because, the classical assumption was incredibly straightforward.
Yeah.
Heat an object, its electrons vibrate, and they emit light.
Right. Simple enough.
Yeah. And the hotter it gets, the faster they vibrate, producing higher and higher frequencies of light, like infinitely.
But when researchers actually ran the experiments, that infinite ramp up just didn't happen. As frequencies got higher, moving up into the ultraviolet range, the light intensity didn't keep skyrocketing.
It just stopped.
It peaked. and then just plummeted. Classical physics had absolutely no mechanism to explain that sudden drop-off.
Wow. So, how did we fix the math to match physical reality?
Well, by completely redefining the nature of light. Instead of treating light as a continuous flowing wave, physicists realized it had to be made of individual, discrete packets of energy.
Okay, let's unpack this. So it's like a vending machine that only accepts exact change, not a continuous stream of water from a hose.
That is a great analogy, yeah.
Mm.
We call these exact change packets quanta, or photons.
Hmm.
The energy of each individual photon is locked to its frequency. A high-frequency photon simply carries more energy.
I mean, you can't just have like half a photon. It's a discrete unit.
Exactly. It's a rigid rule. And here's where people usually get tripped up. If you make a beam of light brighter, increasing its intensity,
You aren't giving the individual photons more energy.
right, you're just shooting a larger total number of photons at the target.
Wait, if we're suddenly saying light, which we always thought was a wave, is actually acting like a discrete stream of particles, I mean, doesn't that imply the reverse could be true?
Oh, you mean could physical particles act like waves?
Yeah.
That was the exact logical leap Louis de Broglie made. He figured if the universe has this underlying symmetry, matter itself should have a wavelength.
And did they prove that?
We saw this happen experimentally when physicists fired a beam of electrons through a tiny crystalline structure of graphite.
Okay.
Instead of just hitting the detector straight on like physical bullets, the electrons interfered with each other, creating a ripple-like diffraction pattern.
So the particles were literally waving through the microscopic gaps.
Yeah, exactly.
And since the wavelength of an electron is radically smaller than the wavelength of visible light, I mean, why care? Is that how the electron microscope works?
Up to 10,000 times shorter, yes. That's exactly why we care. If we used visible light, the waves are too big. They just wash right over tiny structures.
Makes sense.
But because electrons have this incredibly tight wavelength, we can bounce them off something as small as a single red blood cell and get highly magnified, crisp details.
Now, we've talked about particles acting like waves, but seeing the other side of that duality, light acting as a physical particle when it actually hits matter, that brings us to the photoelectric effect.
Right.
This is what happens when you shine a light on a piece of metal and the collision literally knocks electrons out of the material.
Under the old classical theory, if you shone a really dim light on that metal, the assumption was that the electron would just sit there, slowly absorbing that weak light like a sponge.
Just taking its sweet time to build up enough energy to finally pop loose.
Exactly. But the reality is a complete surprise. The emission is actually instantaneous.
Instantaneous. But there's a massive catch, right? It only happens if the incoming light hits a specific frequency threshold.
Correct.
If the light frequency is too low, you could blast the metal with an intensely bright spotlight for an entire century and not a single electron will budge.
Going back to your vending machine analogy, it needs one specific high-value coin to release the snack. A massive pile of pennies won't trigger the machine.
So what does this all mean?
Well, it captures the math that won Einstein his Nobel Prize. He proved that the energy of the incoming photon has to at least equal the metal's work function.
Work function. So that's the absolute minimum energy required to rip an electron free.
You got it. If the photon doesn't have that exact change, the transaction is denied. If it has extra, the leftover energy simply becomes the kinetic speed of the escaping electron.
And this isn't just theoretical textbook math. That exact change threshold is why your phone's digital camera sensor works.
Yeah, and how grocery store doors know you're there.
Oh, wow. And it's how the solar panels on the International Space Station convert sunlight into raw power. The photon hits, the exact change is accepted, and an electron is set free to do work.
The macroscopic world you interact with every day is entirely on these invisible microscopic rules.
Which brings up a completely wild implication for you, the listener. If wave-particle duality means all physical matter has a wavelength, not just electrons, but all matter,
That means you have a wavelength.
you are literally a wave. So the next time you walk through a doorway, ask yourself, why don't you notice yourself diffracting and spreading out like a ripple in a pond?
Now that is a fun one to chew on.
Think about that quantum mystery for a while.
Okay, let's go to step 10, MCQ. Create 2 MCQ at a time without answer. Okay, follow the drawer. I need 10 MCQ. Okay, let's do it. We are a bit late, so let's do quickly. Let's do row 1 and row 2. No, question 1 and question 2. Xingling and Aiden, you can type in. Why did scientists begin to question classical physics in explaining light? Okay, what is the answer for question 1? Which scientist introduced the idea that energy is emitted in a small packet of quanta? Okay, Xingling is typing. Aiden, hurry up. We are late, so we need to complete step 10 as soon as possible. Number 1, number 2. Number 1 is Aiden, you're still with us? Need you to type. Yep. Tell me the answer if you have the answer now. B, or you can type it inside the message. Okay, what is number 2? Remember the story? What happened when the black body dropped down and what he does? C? Okay. Yes, I think it's C also. Tell me if the answer is correct. Oh, both correct. Okay, yes. So question B, question 3 and 4. Let's do it. What happened to photon energy when the frequency of light increases? C and B. Oh, you're fast, Xingling. Aiden, C. Also B. Okay, let's do it. Let's see. Both correct. Great. 5 and 6. Which statement best explain wave-particle duality? Okay. C and B. What about Aiden? Also? Okay. Next one. Correct again. 7 and 8. What is meant by the threshold frequency of photoelectric effect? B and B. Okay, I think it's B also. Okay, Aiden. B and B and C. Shall we try? All right. Last set. Yep, Aiden, I saw it. C. Thank you. 9. Okay, 9 and 10. According to Einstein photoelectric theory, one photon transfer is energy to C and C and A. Is it A? This E equivalent to mc squared is a famous Einstein equation, but whether it is Einstein photoelectric equations. Yep. I think it's B. Okay, Aiden, I think it's not A because we never learned E equivalent mc squared for the past 2 hours. All right, so excellent. Some of you got 9, some of you got 10. So thank you very much. In just 2 hours, now it's 8:11. So 2 hours and 11 minutes, we are able to understand quantum physics well at level 9 or 10. Right, but Xingling, I need to tell you one thing. This doesn't mean that you are ready for SPM. If tomorrow you are going for SPM, it doesn't mean that you are ready. These 2 hours and this 2 hours, we only spend 2 hours, right? The 2 hours is to equip you to have a foundation, a well understanding about what is this chapter about. To be exam ready, you need to do more past year questions. And when you're doing this past year question, just remember that question is related to which drawer. Once you remember which drawer, then you'll be able to remember the picture of the drawer. Remember the story of the drawer. And that story of the drawer is able to give you the information that is related to the drawer so that you can use this information and answer the questions. Right? So as of now, if you go to SPM exam tomorrow, most likely you're not going to do well. You need to be exam ready. Exam ready is what I told you just now. Right? And that takes time and takes a bit of effort. But this is a fundamental to help you to reduce the effort or to make it easier for you to do this revision and also past year question to let you be exam ready. Okay. Same goes to Aiden. Aiden is not taking SPM, but it's the same concept, whichever exam that you are taking, right? So thank you very much. Let's hope we can meet next week, if not the week after, because next week is a holiday. Let me see whether I'm in Saudi. I'm around. Okay, thank you. Bye bye.